Okay, so we're going to go through the last couple activities that we didn't get to in lecture. So, first of all, this one. So we decided not to worry about this one, so you're not responsible for Newton's law of viscosity, which is this thing right here. You should know, though, that, when you have viscous fluids, they flow in sheets. The flow is very regular. They move past one another, and the reason they do that is because a viscous fluid has a lot of friction. So if you have fluid in a pipe that's dominated by viscosity, the fluid is not going to flow at a uniform speed. So the fluid that's touching the walls of the pipe isn't going to move at all because it's basically stuck there, and then as you move closer to the center of the pipe, the flow rate increases. So you've probably noticed a similar phenomenon in a stream or river, like if you've ever been canoeing. So if you want to paddle upstream, you've probably noticed that the fluid is going really fast in the middle, and near the banks it doesn't flow so quickly. So you should probably, if you want to paddle in this direction, you should probably put your boat here versus in the middle, because you'll have less work to do. So a particular application where this is important is flow in tiny tubes. So if you have viscous flow in a capillary, for example, in an artery or a vein, to get a viscous fluid to flow through a little tube like that, you have to apply a pressure difference. So to calculate the fluid flow through a little tube, you're going to use this equation. And I'm just going to do a terrible job pronouncing his name. So what I usually call this equation is just the tiny tube equation. Because I find it much more, well, it tells you what it is, right? Okay. So if you want the flow rate through a little tiny tube, it's going to depend on some geometrical factors, like how long the tube is, the radius of the tube, the pressure difference you apply across the tube, and this pi/8 thing. Oh, and the viscosity, obviously. So this is telling you that if you have a really viscous fluid, so if viscosity is really high, what happens to the flow rate? Well, the flow rate should go down. So this means that if you were trying to, for instance, drink from a straw, right? So you have two cases. You've got a glass of water here, and then someone poured you a nice glass of honey. You stick your straw in there. Maybe you're having a good day and you use a curly straw. Both cases. And so you have to get the fluid to flow through the straw, you have to suck on it. And you're going to have to suck a lot harder to get the honey to flow through the straw than to get the water to flow through the straw. That's what the tiny tube equation tells you. Okay, so what are the applications for veins and arteries? Well, if you have a blood vessel that has a normal healthy blood vessel that doesn't have a lot of plaque buildup, let's say it has a radius r old, but then a lot of plaque builds up and now the radius has decreased, so all of this is plaque, so now the radius is very small, so you have a new radius. And maybe the new radius is half the size of the old radius. So if the radius is reduced by 50%, then that means that r old is twice the new radius. So how is that going to change the flow rate? Well, notice here that the flow rate depends on r to the 4th power, which is a very large power. So we're keeping everything else the same. The only thing that's changed in these two cases is the radius. So we've seen the radius go from r to 2r. Oops, sorry. It's gone from r to r/2 because it got smaller, right? So the new radius is smaller. So that means that Q is going to go to 1/16 of the old Q. Let's see how I know that. So if we just write down, let's forget that. Let's write down two different Q's. So we'll have our Q old. Our Q old is pi over 8 delta P over eta L times R old to the 4th. Our new flow rate is same things out here. That's an L. Times, now our R new is the old R divided by 2, and we're going to raise that to the 4th power. So if we rewrite this, let's pull pi over 8 delta P over eta L times R old to the 4th, and then we have this factor of 1/2 to the 4th. So this is Q old, and this is 1/16. So that tells you that our new Q is a 16th of the old Q, which is a huge decrease in the flow rate. So what happens in the body is the flow rate isn't actually going to change by that much because you still need to get blood to your body. So what does your body do? Well, the pressure difference here, delta P, is supplied by your body's pump, which is the heart. So that means that if the flow rate goes way down because R has gone down, so your body wants to keep the same flow rate. So your body wants to keep this constant. But the radius has gone down. That means that your heart is going to increase delta P to try to keep Q constant so that you still get oxygen to all your cells and all that stuff. So increasing this delta P puts a lot of strain on your heart, and that's not so good. So a lot of applications of fluid flow in medicine. Okay, so this problem, it's not really a bonus. It's a bonus during lecture, but it would be feasible on an exam or something like that. So in this problem, we have a large tank of water with a height 10 centimeters, and then there's this little tiny tube that's allowing the tank to drain. And they want us to find the flow rate Q in the tube. They tell us the density and viscosity of water. Okay, so Q is our equation above. Okay, so we know eta and we know L is a meter, and we know the radius of the tube is a millimeter. So the only thing we don't know here is delta P. So delta P, the pressure difference across the tube, is what's going to cause the fluid to flow. So we need to look at the pressure just inside the tube, let's call that P1, and we need to look at the pressure just outside the tube at P2. And we need to take the difference between them. So we have to find delta P, which is P1 minus P2. Since the water's flowing this way, we know that P1 has to be bigger than P2. Okay, so we need to calculate that. What's P1? P1 is at the bottom of this tank. The pressure at the top of the tank is atmospheric pressure. So P1 must be P ATM plus rho GH, because we've gone down a depth H from the top. P2 is outside the tube, so it must be atmospheric pressure. So if we want to calculate P1 minus P2, P1 is P ATM plus rho GH. And we got to subtract off P2, which is P ATM. So the P ATMs will cancel, and we'll just get a delta P of rho GH. So all we have to do is go ahead and plug this in here, and then we would be able to calculate a number for the flow rate. Okay, so let's see what's next. So the Reynolds number. So if you want to know the qualitative properties of some fluid flow, you could figure out what they'll be by calculating the Reynolds number for your fluid flow. So the Reynolds number is the density of the fluid times the characteristic speed, either of the object moving through the fluid, or maybe the object is stationary and the fluid is flowing past it, whichever speed makes more sense. Eta is the fluid viscosity, notice that's in the denominator. And L is the characteristic length of the moving object or moving fluid. So that means, like, if you have fluid flowing through a pipe that has a diameter d, d is the appropriate length scale. If you have something swimming through a fluid, so say you have a fish that looks like this, and it's swimming through a fluid, the relevant length here is going to be the width of the fish, because it's whatever's perpendicular to the way the fish is moving. So if you had another fish, maybe you had a puffer fish that looked like this, and it has the same width as this fish, but shaped a lot differently in the other direction, and it's swimming this way. Those two have the same length scale because it's the cross-sectional length that matters. So if your Reynolds number is less than 1, we characterize that as viscous dominated. Otherwise, inertial mass is dominating. Okay, so let's show that the Reynolds number is dimensionless. So the Reynolds number units are going to be the units of density. So that's kilograms per cubic meter times the units of speed, meters per second, times the units of length, which is meters, and divide by the units of viscosity, which are kilograms over meters times seconds. Okay, so there's a 1 over seconds on the top and a 1 over seconds on the bottom. Kilograms will cancel. And then this is 1 over m over 1 over m, so all the m's cancel as well. So we're just going to get 1. So it is, in fact, unitless. So you probably all remember way back in one of the early lectures of this course, we had an expression for pressure drag, and we had an expression for viscous drag. So let's find the ratio of pressure drag to viscous drag. So pressure drag, let's call it F pressure, over F viscous is 1/2 CD rho A V squared over 6 pi eta RV. So if we want to do this for a sphere, the cross-sectional area of the sphere is pi r squared. So here we get a lot of things canceling. Pi's go away. One of the r's cancels, one of the v's cancel. And I'm just going to write this again. So we're going to get 1/12 CD rho RV over eta. Now look at this. This is density, length, speed over eta, which is exactly what the Reynolds number is. So the Reynolds number can be interpreted as telling you whether pressure drag dominates or viscous drag dominates. If you get a Reynolds number that's really, really small, that means that viscous drag is a lot bigger than pressure drag, and so you know that your viscous drag dominated. And that makes sense over here. If eta is really big, this number is going to be small, and that's telling you that the eta is the thing that's more important. So if you get a low Reynolds number, that means that eta is more important. So equations that we should use at low Reynolds number should always depend on, well, they should depend on eta. And equations that we should use at high Reynolds number will always depend on rho. So it's often the case that both pressure drag and viscous drag are present, but one of them is much more important than the other. I understand this is a little bit more qualitative than other physics we've seen, but that's because this stuff is really complicated, and so we're kind of forced into a bit of a qualitative regime. Okay, so let's try some practical calculations. So if we were to estimate the Reynolds number for a human swimmer, say, okay, we need the density of water, which is 1,000 kilograms per cubic meter. And the speed of a human swimmer is about 1 meter per second. And the cross-sectional length of a person is, I don't know, it's on the order of like some fraction of a meter. And then we gotta divide that by the density, or the viscosity of water, which is pretty small. And if you do out that math, you're gonna get 10 to the 5th. Now, let's do the same thing for a bacterium. So in that case, the bacterium is also swimming in water. So we still have the density of water, but the bacteria's speed is going to be much smaller. It's 30 microns, which is 3 times 10 to the minus 5th meters per second. And bacteria are very small, so they're, about a micron. And they're still swimming in water, so we have the same viscosity down here. And so you get a very different Reynolds number. You get a Reynolds number that's on the order of 10 to the minus 5th. So contrast these two. This is a person swimming in water, and this is a bacterium swimming in water. So this one is viscous dominated. This one is pressure drag dominated. So notice that's two things swimming in the same stuff, but this one is a lot smaller and it goes at a much smaller speed. If you wanted to feel like a bacterium, you could go ahead and you could get some super viscous fluid. So you could try, for example, swimming in honey. That would make you feel more like you were a bacterium. Because you would be replicating you could replicate a similar Reynolds number by using a much more viscous fluid. So this is also the reason why bacteria don't have wings. You don't see like little amoebas running around with like flappy wings, right? You don't see that because suppose you were swimming in honey and you tried to use wings to move through the honey. Well, when you moved your little wings up, your little body would move down, and then when you move your wings down, your little body would move up, and you would just stay there going, and you wouldn't move anywhere. And so that's why bacteria have developed things like little corkscrew tails, and they just spin the corkscrew in one direction, and that propels them forward, similar to how you would open like a bottle of wine with a corkscrew. You turn the corkscrew, and the cork moves through that material. I would not say that cork is, well, it's definitely more viscous than not. But that's why they have different ways of locomoting, because they essentially are, it's like you would be trying to move through honey. Okay, so to calculate the Reynolds number, we need to know the speed v. If we don't know the speed, then you're out of luck. There's really just not much you can do. And I think that brings us to the end. It does. Okay, I hope that was helpful.